Like this is not like it's not yeah. It was like I'm not sure. So I ordered one like I like I don't know if it's even really when I go to the restaurant, so I'm going to try it. My friend yeah. That's the same. So like right. Yeah. Yeah. I know.
I just want to go over the calendar real quick, just kind of give you an idea of what's coming up. So we have two more new topics to go over. I think I may just do slope fields today, and then inverse trig antiderivatives tomorrow. And then we'll just do differential equation practice at the end of each class. And then Friday we'll devote to solving differential equations. And then I can also I'll give out the test review. If not Friday, then Monday. I will also have all the grades updated by tomorrow. So I'll have the newest or the most recent logs, integrals, exponentials quiz. I'll put that in a grade book tomorrow, and also your calculated FRQ. I'll also have that. I should have that in a grade book by tomorrow. And then I'll give back your quizzes on Friday. So you can look over it, make sure you understand, because those topics will show up again on the test. And then we'll have Monday, Tuesday, and we'll start reviewing on Friday. So Friday review, Monday, Tuesday, and then Wednesday, I need to start the next unit, but we can spend Wednesday end of class or halfway through class continue to review, and then your test will be next Thursday. And I'll have all the test topics up on the board so you know exactly what to study for. So it's topics for your quiz, plus solving differential equations, slope fields, and inverse trig. So today we're doing slope fields. You guys can go to page 7. I don't think this will take very long, so we can use the second half of class to review or continue to practice separating variables or solving differential equations. So slope fields is a graphical approach to look at all the solutions of a differential equation. So we've been solving differential equations, going through our process of separating variables, taking the antiderivative on both sides, and getting our derivative up to the function level. So differential equation is just another word for derivative. But not every derivative can be solved algebraically by hand. And slope fields, what it does is it allows us to look at what the solution would be if we could solve it. Now for our purposes, we're not going to have to worry about, oh wait, this differential equation can't be solved. I got to look at slope fields to see what it looks like. It's more like we just have to be able to interpret slope fields. That's really our purpose. But in the larger context is that slope fields can be helpful for differential equations that cannot be solved. But for us, if I give you a differential equation to solve, it's solvable. You're not going to be given one that you can't solve and you're working on it and you realize that you can't solve it. So the same thing on the AP exam. If they give you a differential equation to solve, it's solvable and there's a solution available. So slope fields consist of short line segments that represents the steepness sketched at many different points. these line segments are tangents to a family of solution curves for the differential equation at various points. The tangents show the direction in which the solution curves will follow. So basically, we're using the derivative equation to gather information about the steepness at every single point. And if we can gather the steepness at every single point, we can get some visual idea how the actual graph is going to rise and fall. Slope fields are useful in sketching solution curves without having to solve a differential equation or without having the ability to solve differential equation algebraically. So here are the steps. We want to identify order pairs indicated on the graph. Plug in the order pairs into the differential equation. Again, differential equation is just another word for derivative. Sketch short line segments to represent the slope through the given point, and then repeat this for all the remaining order pairs. We use the differential equation to find the individual slope segments, which creates a slope field. And then we use the solution of the differential equation to match with the shape of the slope field. So this, I'll come back to this when we can see this in a more, when there's something more concrete to compare to talk about. So example 1, it says, sketch the slope field for the given differential equation at the indicated 8 points. So I'm going to indicate what those points are. So let's just identify those 8 points that you see that are highlighted on the graph. So we have -1, 2, -1, 1. Let's list out all the order pairs that we're going to be looking at. So we have a differential equation, x minus 2y. Again, this is our slope formula for our derivative. Okay, so let's start off with order pair -1, 2. So -1, 2, let's find that on our graph. -1, 2 is over here, this upper corner here. So we're going to insert -1, 2 into the derivative and get a numeric slope representation. So if I plug -1 in for x, I get -1. Plug in 2 in for y, I get 4. So -1 minus 4 is -5. And so we're going to do the best of, to the best of our ability, we're going to sketch a slope that looks like -5. Again, the accuracy is not that important on the AP exam. As long as you have a general feel for what that slope looks like, you'll get credit. It's not like you're going to be graded on how accurate your slope is. -5 is a pretty steep slope. So we're just going to have to do a short line segment that represents that negative steep slope through that point. That's all. So your -5 will probably look a lot like your -6 or your -7. So it's not that important how accurate it is, as long as basically that, if you have a negative slope, that's pretty much good enough. All right, so -1, 1, next order pair plugs in for x and y. So -1 minus 2 is -3. So -3, I'm going through this point here. I'm going to make the steepness a little less steep than this, but still a negative slope. And we're just going down the line and identifying all of these slopes. Okay, so -1, 1, -1 in for x, 1 in for y, -1 minus 2. Oops, sorry, I copied it wrong. It's -1, 0. Sorry, this order pair, -1, 0. That's -1 minus 0, which is -1. So a -1 slope through that point. All right, so you can fill out the rest of these order pairs here. Okay, any questions there? Now, the hope is that after we sketch these slope fields, we have an idea how the actual graph will look. But the issue is that we only have 8 points, so we're not really going to be able to see this graph kind of take shape unless we were able to create a slope field with hundreds of points. But you're not going to be expected to create a slope field with hundreds of points. It's more like, a slope field will be already created for you, and you have to go through the interpretation of it. We'll see that on the next page. But on the AP exam, on the quiz, the most you'll be asked to create is maybe 8 to 10 points. Okay. Okay, let's go through these. I added another point here, 2, 1, just to kind of give you some, there's 2 specific scenarios that I want to show you. So I want to include that 2, 1 as well. Okay, so same steps. It's just now we have a different differential equation. So we're going to take our corresponding order pairs, plug into our derivative to get our slope, and then translate that slope to a slope segment, to a short line segment. So if I plug -1 in for x, 2 in for y, I get 3 halves. So I'm going to try my best to sketch a slope that represents 1.5, which is just a positive slope. -1, 1, slope of 3. Just try my best to sketch a slope that represents a steepness of 3. Again, accuracy is not that important. -1, 0 is undefined. So this is something that we got to be careful with. With undefined, you're going to leave that space empty. So you're going to leave this space empty. I think the natural tendency is students feel like, oh, undefined slope, they want to do a vertical line, but the vertical line is not how a slope field is going to look. It's going to look, so just make sure. I think that's the biggest mistake students make is they see undefined, they want to do a vertical line. So remember to leave undefined empty. So undefined just means something divided by 0. If I have a non-zero divided by 0, those are left empty. Okay. -1, 1 will give me a -3. -1, -1 will give me -3. 1, 2 will give me 1/2. Order pair 1, 1 will give me 1. And then again, empty for 1, 0. So both these order pairs are left empty. Okay, 1, -1 is -1. And then if I plug 2, 1, again, I added another order pair just for demonstration purposes. If I plug 2 in for x and 1 in for y, I get 0 over 1, which is 0. How does 0 look? How would I represent 0? How would my line segment look? Yeah. So 0, that just means slope 0. So slope 0 would just be a horizontal line. So there's four options here, either a negative slope, a positive slope, slope zero, or slope undefined, which is empty. So pretty much you only have four options to work with. So as long as you know how to interpret the slope zero and slope undefined, I mean, these should be easy points. All right, so this is not really going to give us an idea how the graph could look. But let's see what a slope field looks like if these were filled out across many different points. Okay, so this is a better representation of what a full slope field would look like. You have hundreds of points all filled out with different slope segments. And it says, determine the equation that's being graphed by each of the slope fields, then sketch a solution that passes through the indicated point. So if we were to start at this point, these are many different types, many different functions that all are in the same family, but just with a different y-intercept. So if I start with this point and I just kind of follow the flow of this graph, I can kind of see how this graph could look like. Obviously, if we had a different starting point, then it would just be a translated version of this graph, right? Basically, all the graph will look the same. It's just that, you know, some will be higher up than others, but we want the graph to go through this specific point. So if we're trying to match this with the slope with the appropriate derivative, I mean, we wouldn't want to do this. We wouldn't want to build every slope field from scratch, plug in 0, 0, plug in 1, 1, and then create 5 different versions of the slope field of these and then match with this one. That would take too long, right? So the idea is we want to identify a couple of characteristics. Whenever I see these types of problems, I always think about what can I do to eliminate the wrong choices. I like to eliminate the wrong choices rather than looking for the right ones. If I can eliminate, ideally, if I can eliminate 4 wrong choices, then the one that's left standing must be the right one. So here are the 4 things that I look for. Let me identify those things here. The 4 things I look for is, where do I see a collection of slope zeros? If I see an entire part of the graph that's showing slope 0, then that can help me narrow down my options. Next option, or next thing I'm looking for is, where do I see slope undefined? So slope undefined would be you see a huge gap in your graph. If there's a huge gap in your graph, that means, okay, at this X or Y value, the slope is undefined, and that usually can help me eliminate some choices here. Next one, where do I see a collection of positive slopes? Maybe the entire first quadrant is positive slope. That means, okay, that means any order pair that I plug in the first quadrant into my derivative, I should get a positive number in return. If I don't, then maybe that can help me eliminate some wrong choices. And finally, where do I see negative slopes? And usually, if I can identify places where the graph is showing me slope 0, slope undefined, positive or negative slopes, that should allow me to eliminate at least a couple, if not all the wrong ones. So look at all these slopes that you see in front of you. What do you see mostly? Do you see mostly slope zeros? Do you see mostly slope undefined? Do you see mostly positive slopes? Or do you see mostly negative slopes? Positive, right? So pretty much, right, the entire graph is positive, which means that no matter what order pair I plug into my derivative, I should get a positive in return. So that's one observation that I make, right? It's mostly positive. So every order pair should give me positive number, but do I see something else other than positive slopes? What else do you see? Slope zero, right? So where do you see slope zeros? When what? What variable? It's the y-axis, right? So when what? When x is 0. So that means if I plug 0 in for x, I should be guaranteed to get a 0 in return. Okay. So let's go down these options here and see. All right, is this always going to give me a positive in return? X cubed? No, right? If I plug -1 or -2, I'm getting a negative number. So if I were plugging -2, I should be getting a negative in return, but I don't see any negatives here. So I know this one is out. 3x squared. Is this always positive? What do you guys think? Always positive, right? No matter what x value I plug in, if I give it a positive x, it'll return me a positive y value. If I give it a negative x, that squared will make it positive. So this could be potentially the right answer. So we'll leave this one alone. We can come back to this one if we're down to a couple of choices. 2x plus y. Is this always going to be positive? No, right? You can imagine getting a negative y value or negative x value that could cause this to be negative. And we don't see any negatives here, right? So this one is out. Is x over y always positive? No, right? If I have a negative over a positive, that's negative, or a positive over negative, that's negative. Natural log of x. Natural log of x is always positive, but natural log doesn't exist in the negative regions, right? Natural log of -1 doesn't exist. So if it's natural log of x, this whole thing should be empty. But there's only one option left, right? 3x squared. And if I plug 0 in for x, I do get 0. So that's something. So typically, though, this strategy is not always going to get you down to the right answer. But this strategy of looking for wrong solutions typically will eliminate a good chunk where you should be able to get it down to 2 choices. And then between the 2 choices, you can look at it more carefully to see, okay, which one will be the better fit. Now, how is this curve related to a 3x squared, right? Because 3x squared, we think that's a parabola. So why is the graph not matching? Well, this is talking about this is describing the slope behavior, but the graph you see in front of you is a solution to this curve. So this is more at the function level, and then the individual slope segments is at the derivative level. So if we were to solve this differential equation, it should match the shape that we see in front of you. So why don't we step to the side and solve this differential equation and see what we get and see if that will line up with the graph that we see in front of us. All right. So let's try that. So dy over dx is equal to 3x squared. I'm going to make that 3x squared over 1. I'm going to force a 1 below. I'm going to go through my process of separating variables, cross multiplying. Okay, cross product. Okay, 1 dy equals 3x squared dx. The first thing that we always do is look to see, do we have our dy dx's in their right places? We do. And next up, do we have full separation? Are the x's together? They are. Are the y's together? There's only dy, so that's fine. So we're ready for our integral. Okay. What's the integral of 1 turn into? 1 becomes what? It's in terms of y here. So 1 just goes up to what? Just y, right? Antiderivative, we make our degree rise by 1. 3x squared, we go through power rule. This becomes 3x cubed over 3, and then plus c. So y is equal to x cubed plus c. And this matches the graph we see in front of us. That plus c just indicates a different y-intercept. So x cubed plus 2, x cubed plus 5, x cubed minus 2. All those graphs are represented here. That plus c will just shift the graph up or down, but we see a cubic function in front of you, and the solution to the differential equation is a cubic function. So the derivative, the 3x squared is helping us describe the slope at each of these points. And the solution of the curve is matching the shape that comes out of all those slope mixed or put together. All right, next up, number 3. Again, we're trying to match the differential equation that could fill out this graph the way that we see it. So again, we would like to look for 4 things. Do we see slope zeros? Do we see any slope undefined? Do we see positive slopes? Do we see negative slopes? And here, we do see slope undefined, right? All this is empty. So we can make that note that when x equals 0, which is the y-intercept, our slope is undefined. Which means if I were to plug 0 into the derivative, I should get a 0 in the denominator and get me something that is undefined. Now, there's something tricky about the x-axis because the x-axis can either be slope, can either be slope undefined, or it could be hiding what? It could be hiding slope zeros. So we just have to be careful that sometimes your x-axis is not as helpful as you would like because maybe it's hiding a slope 0 that you're not seeing because it's covered up by the x-axis. So sometimes we don't want to make assumptions with x-axis. If we don't see a diagonal slope coming out of it, just be aware that it could mean that slope is 0 or a slope undefined. So we'll put the note there, but just be aware that we have to leave that. We need to leave room for flexibility because we don't know exactly what's going on there. So when y equals to 0, maybe it's slope 0, maybe it's slope undefined. Okay, we don't know, but it's still helpful to have those 2 options. All right, moving on to positive and negative slopes. Where do you see positive slopes? Is there a general place that you see positive slopes? Yeah, I see first and third. That's nice, right? We have a nice, easy spot to fill out positive slopes. So any order pair that's in the first and third quadrant should always return me a positive dy dx. Right? So that's really helpful. That should allow us to eliminate a bunch of wrong choices. And then where do you see negative slopes? Quadrant where? 2 and 4, right? All right, so let's go down and see if we can eliminate the wrong choices. That can't be the answer. So dy dx equals x minus 2. When x equals 0, slope is undefined. If I plug 0 in for x, I'm not getting undefined here, so this can't be it. When x equals 0, slope is undefined. When x equals 0, that's not undefined slope, that's slope 0. If I plug 0 in for x, I'm not always getting undefined. Could be 0 minus 3, could be 0 minus 4. So this one could work, right? When x is 0, slope is undefined. When y is 0, it could be slope 0. When I'm in the first and third quadrant, positive over positive, or negative over negative, that will always return me a positive number. Negative slopes in second and fourth quadrant. If I do positive over negative or negative over positive, that's negative. So it looks like this could be a good fit. All right. And then for E, when x equals 0, slope is undefined. There's not even a place for x, so there's no way this can be undefined. But there's not even a place for x. And also, e raised to anything is always positive. There's no negatives at all, so this kit doesn't fit. So that's nice. We can eliminate all the way down to. Now, if we were to sketch a graph through any of these points, maybe I'll just pick this point here, right? We see a bunch of lines, right? So if we were to solve this differential equation, we should get something that is representing a linear function. So let's practice solving this differential equation and see if we get something that resembles like a y equals mx plus b sort of equation. Okay, so, oh, we'll use the space for number 4 since we won't do these examples. So let's use that space for solving this differential equation. dy dx equals y over x. Okay, we want to solve this differential equation algebraically, so let's cross multiply. Again, when you cross multiply, you're just doing it blindly. You're not trying to get everything lined up. You just want your dy dx's lined up. That's all we care about. So don't feel like, oh, my y's and x's are out of place. If it is, it's okay. We'll take it one step at a time. But don't try to do too much at once. So I typically like to cross multiply in a way where my dy will end up on the left side and my dx is on the right side. So that's these are my anchor variables. I want these to be in their right places. And now we can ask ourselves, are the x's and y's separated? Not quite, right? The y's and x's are mixed, but we know that we're not going to move these two. These two are set in stone. If anything, we have to move the x and the y. So whenever you see something that needs to be moved, try to identify all the things that needs to be moved and just move everything at once. Don't try to move one thing at a time because then algebraically it just gets more complicated. So I see the x has to move and I see the y has to move. So I'm going to do a double division. I'm going to make both things move to the opposite sides and go to their respective denominator space. Okay. That just makes it easier. So this will go below here and the y will go below there. So I have dy over y is equal to dx over x. Okay, don't be afraid to put x's and y's in the denominator. We have rules that can handle them. A lot of students don't feel comfortable with this, so they end up putting the y and x up back in the numerator, and then that changes your entire algebraic equation. So, trust your algebraic steps, right? If something needs to be moved over, put it in the denominator. You can handle variables in a denominator. So this ends up being 1 over y dy, which is natural log, and this ends up being 1 over x dx, which is also natural log. So we're applying natural logs on both sides. 1 over y is natural log absolute value of y. 1 over x is natural log absolute value of x. And then we save the plus c just one time on the right side. Okay, I want to solve for y, but y is stuck inside natural log. So I'm going to raise both sides with e as the base. Drop the natural log. I have absolute value of y is equal to. And I want to separate these exponents with the c away from the variable. So I'm going to say e to the natural log absolute value of x times e to the c. We know e to the c is just one giant c times c. And I know that e in natural log cancels out, so I can also drop the x down. So I have absolute value of y is equal to c times absolute value of x. Both the absolute values can be sucked in. The plus and minus can be taken by the c. So I have y is equal to cx. And y equals cx is basically a linear equation, right? It could be y equals 3x, y equals 4x, y equals negative 2x. And those are all represented by all of these diagonal lines. So the solution to your differential equation will match the flow of the graph, but the derivative will tell you information about the individual slope segments. Okay, I like to use the remaining time that we have just to do some additional solving differential equation practice. So let me pick out a page that we can do that on. Let's go to page 18. So we know y prime can be represented as dy dx. And then our initial goal is to try to get the two terms to be on opposite sides so that we can cross multiply. Let me rewrite that y prime as dy dx. And I can try to get my two sides to show me fractions so I can cross multiply. So as soon as I cross multiply, I know that my dy dx's are going to be lined up nicely. And then we asked, do we have full separation? We already do. Our y's are together, our x's are together. And there's nothing that we can move over from the right to left. If there was like another coefficient, then I typically want to move it over, but the left side is already as minimal as it can get. So both sides are ready. We're ready to take the antiderivative, move on to our calculus step. So integral. Left side is just an easy power rule, but the right side, we need to do a little bit of what? What's needed on the right side? What process do we have to go through? That's not just an x, right? That's a 3x, so we got to go through what? U substitution, yeah. So it's like a problem within a problem here. So this ends up giving me 2e to the u times du over 3. All right, replace 3x with u, replace dx with u over 3. Pull the 2/3 out. And we know e to the u is just e to the u, right? It doesn't turn into natural log. It's not power rule. E to the u is just itself. So 2/3 e to the u plus c. And then the right side, we know it's just y squared over 2. That's just power rule. So y squared over 2. The result, that left side was a lot easier. So we're spending most of our time trying to get that right side to be cleaned up. And then replace the u back in terms of x. So we're basically at the general solution, but I do want to do some cleanup here before I solve for c. So I'm going to multiply everything through by 2 because eventually that 2 has to come back over to the right side. Distribute everything through with 2. The whole purpose is to get it at least down to y squared. Okay, distribute 2 through, so 2 times 2/3 is 4/3. I could do plus 2c, but I know that c will just take on any coefficient, so I'm going to just say plus c. I think this is a relatively easy equation. Before the square root shows up, I'm going to go ahead and just solve for c at this point. Again, you can solve for c at any moment as soon as c shows up, but sometimes I like to wait a little bit longer until I can get my equation a little bit cleaner so that I can just avoid messier algebraic steps. That's my only motive for waiting to solve for c. If I can imagine the equation being a little cleaner, then I typically want to get it to that point before I solve for c. But you can solve for c at any point in time, and it's not wrong to solve at a different place than me. So I'm going to solve for c at this point. Plug 5 in for y, 0 in for x. Careful that we don't just assume that 0 will wipe everything out, right? E to the 0 is not going to be 0. E to the 0 is going to be what? 1, right? And then 1 times 4/3 is still 4/3. So just be careful that that we don't make too big of an assumption that 0 is just going to make everything 0. So I have my c value. I'm going to update my equation with the c value that I just found. Now I can make my way down to y. My final step is to take the square root. We know, though, that when we take the square root, there are 2 separate functions that shows up. And we only want to choose the one that actually goes through our order pair. And the way we decide is we look at the y value. Whatever the sign of the y value is the sign that we want from our square root. Again, the idea is that if I plug 0 into this equation, I want to get a y value of 5. The only way I'm going to get a y value of 5 is if there's not a negative sitting out here, right? Negative is going to force that to be a negative y value. So I just want an equation that has this order pair in it. Okay, your homework. Look in your Unit 7 homework packet. And you're going to go to page 11, slow fields, and you're going to do page 11 and page 12. Okay, I'll send out a reminder this afternoon, and also send you a link to the key where you can check your answers. Okay, so page 11 and page 12 is your homework. All right, complete your phones.